Okay, can you hear me well? Okay. Okay, so let's recap a bit what we have seen last time, and then we'll move on. So last time we have talked about n-step bootstrapping, and we have started introducing model-based reinforcement learning. We have seen that basically n-step temporal difference methods are an intermediate approach between what Monte Carlo methods and one-step temporal difference methods do. So we have seen this schema that basically generalizes everything from one-step temporal difference to Monte Carlo approaches. Um, then we have said that in n-step methods, generally what we do is computing the target as the sum of the rewards discounted until the end step, where at the end step we introduce the bootstrapping step, where we use the estimation of the value function for the end state. So basically, this is the end step return, and it's computed according to this formula, which I just described. Um, we have seen some properties, some examples related to this. We have seen one specific instantiation, which is n-step sarsa, and also another instantiation, which is n-step expected sarsa. And from this, we started saying that there is a difference between pure sample updates and expected updates. So, for example, in expected sarsa, we have at the last step an expected update where we consider all the possible actions weighted by their probability of being selected according to the policy. Um, okay. We have also seen that we can do n-step temporal difference using off-policy methods, where we compute important sampling ratios in a similar way to what we have seen for um, the case of Monte Carlo methods, except that we truncate the number of steps that we take into account in order to compute these ratios. We have also said in the end, we can do off-policy reinforcement learning in this n-step setting, even even without using important sampling ratios. For example, for one-step temporal difference, we have seen Q-learning and expected SARS, so they don't use really um, these important sampling ratios. So how can we do that? We can basically use um, expected updates mostly, and we can control the amount of sampling or the amount of at which rate we use the expectation by means of some sigma factor that denotes the degree of sampling at every time step. Good morning. Okay, so this is the diagram of what I was just describing. After that, we started saying, um, we talked so far about model-free reinforcement learning, so we assume to not have a model. In model-based reinforcement learning, we still assume to not have a model, but we also say, look, we can learn a model and we can use this for planning while we do reinforcement learning. So we have seen a bunch of schemas um, here of this kind, where we have an agent that acts in the world, collects some experience, and performs direct reinforcement learning. But beyond this, It uses this experience to build a model, for example, using supervised learning, and this model is used then for uh, planning. And you can use many different planning methods. For example, we have introduced one planning method that is queue planning, and we have seen that the Dyna agent, specifically the Dyna queue agent, uh, exactly use the queue learning update rule in order to do both planning and reinforcement learning. And the model learning part instead is a simple table where we assume deterministic environments and we just record the transitions and use them as they come. Um, okay. And this was the pseudocode. And I think we stopped here when I was saying, see, with just few planning steps, we can dramatically improve the number of episodes that are required um, in order to, okay, the number of episodes that are required in order to converge to a low number of episodes, oh, sorry, a low number of steps per episode, which I want to repeat, denotes how good the policy is, right? Because if I need few steps in order to reach the goal, it means that my policy is quite good. Okay, so I think we stopped here. And I want to look also at this slide here, where basically we are showing here the number of states that get some information after one episode of the algorithm. So if we consider without planning, this is basically Q learning. And this is Q learning because we are doing DynaQ without planning. It's pure only Q learning. So the only state that gets some information after one episode, of course, is this one, right? Because we have zero rewards everywhere. Here we have a positive reward. This is the only state that gets a meaningful update because it's the only one that has a connected transition to the goal. If we use this planning method, of course, instead, we'll see that given that we are sampling from this model some transitions, and I mean, we collected these transitions because the agent has done something in the agent. So it was maybe randomly roaming inside this environment, and it went up here, and then it moved down, left, right, back and forth. And then eventually it reached the goal. So I was able to store in my data set, in my table, a bunch of these transitions, and then I was just sampling from this table model. And this allows the algorithm to perform many more updates. So not only am I able to update this state, maybe at the first iteration of the planning. If you recall, in this pseudocode, we have seen that you can do planning for a certain amount of steps. Here we selected n equal to 50. So this means that we are running on our, in a single episode, on the model that we have built, 50 planning steps, which basically is allowing us to compute the Q values for many more states. Of course, and this is a question that also somebody asked last week, models can be incorrect because, first of all, the environment is stochastic, but maybe you observed also a very rare transition, and then you're assuming, for example, in DynaQ that that is the transition. And also, you have only a limited number of samples that you are observing. And so eventually, instead of using a table, you could use a function approximator like a neural network. And maybe generalization is not perfect in that case, or for many reasons you have some error in your function approximation, then this leads to incorrect environments. And also, there are situations where the environment is dynamic and the environment can change. So if we consider the usual example of the robot roaming in this room of the department, um, the environment has just changed because one colleague has entered the room and maybe has moved the chair, for example. So that leads to a change in the environment where maybe the robot before could walk uh, on a specific pattern, but now it can't anymore because your colleague is sitting there. Um, of course, if model is incorrect, planning will compute a suboptimal policy, but this suboptimal policy is not a bad thing because as I said last time, this allows the agent to discover new things and allows, so basically it's doing exploration for us in a certain sense, and um, also allows for the correction of errors because once the agent explores, it collects more transitions and it can improve its model and correct the errors. In general, um, this um, happens specifically if the model is optimistic, which means it predicts a greater reward for a certain state or a better state. And this should, I mean, I think, did you already study A star? Okay, so I mean, this is a similar principle, right? Where you want to you want the heuristic to underestimate the cost of your um, path if you're using the heuristic, but in this case, the cost is the inverse of the reward, so we want to uh, predict a greater reward or better state. Okay, of course, again, the idea is that your policy, the policy that you're planning will exploit the opportunities that will be thought by the agent to be good, discover that they don't exist, and then finally get better, fix the overestimation, and improve uh, the, the policy and the model. So as I was saying, this is a different version of the exploration versus exploitation problem. So you want to you are in favor of having some errors in your model because they allow for exploration. Um, of course, you want to also exploit because you want to behave in the optimal way, given the current model. So we don't want to degrade too much the performance. So there are variations of DynaQ that allow to keep this issue into account. Um, so, for example, DynaQ Plus, it's an algorithm that keeps track for each state action pair of how many steps elapsed occurred since when this state action pair was visited. So the longer the time, the greater the possibility that this has changed, and basically this will allow the algorithm to select this state action pair in order to allow the agent to fix maybe errors or changes. And so let's look at one specific example of this. Let's assume that we have our usual grid word, except that this grid word is changing in the obstacle location. So after a certain amount of steps, specifically here we are considering actually more than steps, probably this is episodes, but anyway, considering this change at 1000 episodes, the obstacle that moves from being all left to being all right. So the corridor moves from the right to the left. You can see that the DynaQ plus algorithm here adapts more quickly, leading to a better performance after the change, of course. Also at the beginning, you can see that the environment improved, the learning is improved in this DynaQ plus algorithm. Again, the idea here is very simple. You just keep into account how many steps occurred since when your agent has visited a certain amount, a certain step, a certain state in action, and in that case, um, you go to select that state in action in order to fix the issue. The issue and improve your model and verify if any change has occurred. Now, you can also see here one other example where the change is slightly different. So the change here is that we are removing one obstacle from the right, which allows the agent to eventually discover a shorter path. As you can see, after this change, the DynaQ plus algorithm discover these changes much faster, and this is why at this point the DynaQ plus curve goes, has a different gradient, which is improving much faster the cumulative reward. So, given that we're saying this, let me repeat a bunch of concepts. So one question that might arise is, what are the metrics that I should use to evaluate my performance, the performance of my agent? So we have seen a bunch of those. And in practice, these are all interesting. So we have seen, of course, the cumulative reward. That is one obvious metric because we are directly optimizing that. So we want to use that um, as our metric. The other thing that we have seen, I was using in another example, is the number of time steps. This depends on the specific task that you are uh, working on, but generally it's a useful idea to verify what is the number of steps that are required by the learned policy in order to reach a specific goal or a terminal state with a positive reward, not a terminal state where you get bad termination. So that's another metric. And we have also seen, in case you have some ground truth, you can use some metric like root mean square error and other standard error metrics. Okay. So one other thing that we could do is that instead of selecting state action pair in a uniform way, we can also think on what are the states that, according to what I'm currently seeing, would change more. So we are considering, let's look at the pseudocode. I think for this, this is more clear in this setting. So if we see in a certain state that this is our error, right? Specifically, this is our TD error. But in general, the error in the that we use in order to correct our estimate is greater than a certain threshold, then we update all the states and actions that are predicted to lead to that state. So this is um, quite an intuitive idea. You simply say, look, in this state, I thought this would have been my value, but in fact, I'm getting a very big correction here. So this means that my model for this, that my learned Q function for this specific state was very wrong, which also means that the value of all the states that lead here is probably very wrong. So I want to correct the value for all the states that lead me here. How do I do this? I just look at my model and I see which state and actions lead to these specific states, and then I correct them. So in this way, I'm I am updating the Q values of those states much more rapidly, and potentially this leads to a faster convergence. So um, if we look at the number of updates until the optimal solution is found, and again, this is another metric if you know what the optimal solution is, because there are many problems where you don't know what the optimal solution is. Otherwise, you wouldn't really need reinforcement learning. But in any case, if you look at the number of updates, you see that there is almost one order of magnitude of difference between using DynaQ without prioritized whipping and using the prioritized whipping, which is the procedure I have just uh, described. Um, so let's see if there are questions regarding this. Uh, this is everything about the homework. Homework. Anyway, yeah, let me answer a few of these. So about the homework, can we help with the code provided on Classroom? Of course. Otherwise, I wouldn't provide it. In the lesson codes, an action is weighted by the probability of whether it will happen or not. But Pacman is precise on actions. Should this thing be removed? So if you're referring to the value iteration algorithm, or I don't know what you're referring to, but of course, if the environment is deterministic, you don't need to do, or actually, you still have the the weighting, but with the weighting is probability 1, so you 0 everything else. I don't know if you are referring to this though, so uh, please clarify your question. Or maybe in the transition function, if you're saying in the transition function, if the environment is deterministic, then you, of course, you don't have any probability. You just need to execute the action. About the is an acceptable approach to create an environment implementing the gym interface, register it in gym and import it with gym make. Of course, yes. In Pacman, should we use as goal the fact that we ate everything in the world, or should we use as termination test just the fact that we hit a ghost? So the goal, yeah, I mean, one thing is you have two termination conditions. One is that you ate everything, and the other one is that you hit a ghost. So they are both termination conditions. Of course, you want to maximize your reward, which will be probably related to the fact that you ate the ghost. Sorry, you ate everything in the word. Is it okay to use the same iterative policy update that you used on the MDP example on Colab? I don't know what you are referring to, but again, here I implemented the value iteration in case you are required to implement, again, that's optional, the policy iteration algorithm. So keep that into account. So here there is nothing new. Any questions regarding what we were talking about now? Is that, do you have any question? Okay. Okay. Okay, so so far we have seen methods that have been performing in this model-based scenario updates on each state. And this is the case, for example, of dynamic programming. But this is problematic, of course, on large tasks because you have many, many states. Many of them might be irrelevant, so you don't really want to think too much about them. But still, with a large state space, for example, if you do value iteration, you have to consider every possible state, and that's very computational expensive. The alternative, the obvious alternative to this is sampling from the state or the state action space according to some distribution. And we have seen, for example, that we can do this in a uniform way, or we can do something slightly different by doing the prioritized whipping updates. The other idea is you can use the on-policy distribution. What does it mean? To follow the distribution of the states that you observe when following your policy. This is very easy to generate. So you sample your action given by the policy, you sample basically a bunch of trajectories, and you use those in order to do your sampling. So um, if you look at the at these other plots, specifically, let's look first at the second plot, where we have we're looking at the value of the start state under a greedy policy, and of course, this is the value at which you want to converge. If you do uniform sampling, then you will see that this is converging much more slowly than following the on-policy distribution. Why? Because the policy is improving. So the intuition here is very simple. The policy is improving and eventually is leading you to the goal state. The fact that it's leading you to the goal state um, allows the updates to be more focused on the states that are relevant and that you are visiting. So if you sample from the from the policy state distribution, you are basically updating states where you have a lot of information. You have a lot of information about this because you visited them several times. So it's easier to update these states. Hmm? So far for the model-based approach, we talked about doing updates in an offline way. What do I mean? Um, it means that we didn't really do anything focused on the current state. We didn't really do anything that was related to the state that we were in. Sorry, let me skip this slide. But so we did background planning. I said offline, but it's background planning. So this planning is not focused on the current state. In other situations, you might be interested instead on planning exactly from the current state. So this is called decision time planning. And in decision time planning, you start planning in every new state. So every time I visit a new state, I start planning from here, and I try to choose what is the best action according to the model that I have to execute in this state. So In order to do this, you use your learn model again, you simulate your experience from the current state, and you select some action. Then you update and evaluate your policy or value functions specifically for the state that you are in. Of course, these two approaches, the background planning and decision time planning, can be unified and blended together. This is very similar to what you do, for example, in heuristic search. Right, in classical AI search algorithms, state space planning, this is exactly what you do. So by now you should have seen all of this with Professor Nardi, and you should know that in practice this is what you're doing in classical planning. So basically, for each state in these algorithms, we evaluate what are the possible continuations. There, we are in practice evaluate. I mean, we are not doing learning, but in practice, we are using some sort of value function that backs up the um, the information for us. The value function is: have I reached the goal or not? And this allows the agents to choose the best action. Um, in those methods, typically you don't have any effort to store or save the value functions or any information related to that. You just do planning at every step. So you don't have any memory that you are using where you keep storage of every search information. You just focus on the current state, you do your planning, and then you forget everything, you discard everything. Um, so this is one example. For example, here you are starting from the state, and then you are expanding all the possible possibilities that you have, and until you find the actions that lead to your solution. So in this, for example, in this example, we are looking at a depth first heuristic search. Also, in these heuristic search methods, typically you don't have a multi-step update, but you do one-step update, similar to, I mean, what we have seen previously. We do just one update from this state to this state, and that's it. This is slightly different when you deal with algorithms that are called rollout algorithms. These rollout algorithms are still decision time planning algorithms, but they use, instead of one-step updates, they use the full Monte Carlo trajectory. So they use Monte Carlo control. Um, so they execute a policy until they reach some terminal state, starting from the current state. Specifically, what they do is they try all the possible actions for a certain state, and then after executing all the possible actions, so let's do one example. I am in a certain state, and I have three possible actions. I will execute action A, and I will then follow my policy until termination. Then I will collect all the rewards. I will back up this information and say, look, if you do this action and then if you follow your policy, this is the value that the return that you will get. Um, then I keep that written in my memory, and I execute action B. And after executing action B, I will follow my policy until termination. I will collect my rewards, I will compute my return, and I will store it in my memory. Then I will do the same for action C. Then I will look at the returns that I got from action A, action B, and action C, and I will choose the best, the action that is leading me to the best return. Of course, now I said I will do this once for every action. In practice, you don't do this once for every action, but you do several times for every action the same procedure in such a way that you have an estimate of your value function. So, well, of course, the value function, again, is the expectation of the returns. So you want to average all the returns that you collect, and this will be an estimate of your value function. That will be the value of taking a certain action and then following a certain policy. Which policy are we following? The policy that we are following is called the rollout policy. It can be, for example, any policy that you want. Specific, maybe um, a fixed policy, maybe a random policy, whatever. That's why you have to uh, do you have to compute the average of the returns over many examples. So again, you will compute these estimates of the value function not based on one single trajectory, but on many trajectories, because you want to compute an estimate of the value of that state by following a certain action. So when you will think that the estimate is accurate enough, then you will choose the action which has the highest value. So what are the difference between this method, this approach, and the normal Monte Carlo methods? First of all, here we're making use of a model, but not only this, in Monte Carlo methods, overall you're trying to compute the optimal action value function. Here you don't care about that. You only want to estimate the value of this state and all its actions. Then once you compute this estimate, you don't really do any updates. You just take the action and you forget everything. So you just make immediate use of these action value estimates, you then discard them, and then you don't have any real value function and policy that you are computing. So the policy is, in this algorithm, is computed at every step. Let's say for every state, the policy is computed by following this procedure. Hmm? Of course, this is assuming you already learned your model, but so this is a planning strategy. So we are now building on the fact that we said we can learn our model using several approaches. You can use any function approximator. You can do whatever you want by collecting experience in the world. Once you have built your model, what is the kind of planning that you can do? You can do planning, decision time planning using rollout algorithms. And in these rollout algorithms, you have to follow this procedure where you don't really follow any specific policy. Your policy will be computed at every state by looking at what are the possible outcomes of following every action. And this idea is based, of course, on the policy improvement theorem. Why? Because if I choose the action which leads me to the best average return, then that's the best action that I can follow according to my current model and my current policy. So Monte Carlo tree search is another algorithm, which is still a rollout algorithm, but it's slightly different in the fact that instead of discarding the estimates, it accumulates the value estimates and it uses them in a different way. So specifically, you are, in this case, trying to compute estimates that, I mean, you're trying to have estimations that directly try to target highly rewarding trajectories. Again, this is done as the rollout algorithms at every new state. And again, by following Monte Carlo tree search, you will have an agent that just looks at the action, at one single action for a certain state. Um, Similar to rollout algorithms, you will have many simulations done from a certain state until a terminal state. Or when I say until a terminal state, you can also do something similar to n-step bootstrapping if you have an estimation of your value function because you want to truncate, for example, your simulation. You don't store the value functions from one action selection to the other, but you do an expansion of a tree. This is why it's called Monte Carlo tree search. You do an expansion of the tree where you are using a value function that you are updating several times. So you, in order to do this, you have a tree policy and you have your rollout policy. Specifically, let's look at this diagram. Let's say you are in this state. You are in this state, and then you want to do your planning from here. So what you will do is selecting all the possible actions, doing all the rollouts, computing the value of each state, and then, of each possible action, and then build an estimate of this value function here. Then after having done this, which is basically what you're doing in one rollout algorithm standard without any modification, you do something more. You expand one specific action, which means you, in your simulator, you say, okay, now I will say, I want to, let's suppose I follow this action. What will happen? So you expand this specific path, which means that you will, in your simulator, again, you will end up in a new state. From here, you will have several possible alternatives, and you will do again the whole thing. So eventually, if you look at the end of this horizon, what you're doing is expanding the actions that you can have, then doing some simulation where you compute all the returns and then backing up this information not only at the end of this tree that you're building, but up to the top according to the policy that you have followed. Now, I don't know, I think I see the only face that I see here is a bit confused, so I want to repeat this. So at every step of this planning algorithm, you have 4 phases. One is a selection phase, one is an expansion phase, then a simulation phase, and a backup phase. In the selection phase, you select a certain action. How do you select a certain action? According to the tree policy. How this tree policy is built, for now, we don't care. Okay? So let's say you have a tree policy, and then this will tell you, okay, this is the action that you should follow. So, for example, you do this in this state, and in this state, and here you have to do an expansion step because your policy says you should follow this action here, but you didn't yet execute this action. So what you will do is expand the tree by adding this node, which is the next state. And from here, you will follow your rollout policy. You will do this several times. You will collect a bunch of returns, and these returns will be summed up with the rewards that you collected in your simulator in every state that you visited according to your tree policy. So this will allow you to update the value of each of the states that your policy has selected, that your tree policy has selected. Okay. Of course, at the beginning, you will start without this tree because you will not have any tree built yet. So you will have all the possible actions. Your tree policy will select one action. You will expand your tree. And then from here, you will do all your simulations. And then you will, by doing all your simulations, maybe you are changing your tree policy. And then by doing this, you're again selecting another action, and so on and so forth. Um, so let me repeat that you are building this tree for one specific state. Then you typically discard the tree, all the tree that you have built or your estimate, you typically discard them at the end of this simulation for this specific state. Then you forget about this, and you will do the same when you reach the next state. Again, all of this is done in simulation. So this is done just for selecting one action. So in simulation, you try all these things just for selecting one single action in the real world. Hmm? So why is this maybe a bit an improvement compared to rollout algorithms, standard rollout algorithms? Because of course, by saving action values during your when building and expanding your tree, you're having a more focused expansion of the tree, and you're focusing on trajectories that have potentially high return trajectories according to what you estimate is. Let me say also that in a bunch of um, in a bunch of implementations of Monte Carlo tree search, you typically store the tree and you reuse that. Okay, so this is another variation that you can have. Now your question might be, okay, but what the hell is this tree policy? This tree policy can be, for example, a UCB1 policy. So the UCB1 policy, we have seen that when we talked about bandit algorithms. So the UCB policy will be a policy that will be um, doing optimistic action selection. And this optimistic action selection is basically based on um, following the best action, so being greedy, plus having an exploration component, where this exploration component is based on the number of times you have visited a certain state and action. And if you visit that many times, then the probability of selecting that state action pair will decrease. If you don't have visited that for a bunch of time, instead the probability will increase. Um, so for example, that will be what you can use for building your tree. Let me see if there is anything I've missed in this description. That might be relevant. Okay. It seems not. So let's look at this last slide for this deck of slides. This is basically a schema that includes all the algorithms that we have seen so far. So you see here at the beginning, temporal difference learning on the leftmost corner up. You will see that we have temporal difference learning. If we increase the depth, so the length of the update, so if we go more in depth rather than in breadth, then you're going towards Monte Carlo methods. Here in the middle, you have n-step bootstrapping methods. If you expand instead on the direction of the width, Here you find dynamic programming, because in dynamic programming we are updating every state based on one single step, right? So we say that we said that temporal difference methods are an intermediate between Monte Carlo and dynamic programming methods. If we go from dynamic programming, which is a planning method, of course, here we are assuming that we have a model in this side of the world, which is the only thing that allows you to go in breadth. Then if you expand not only the breadth, but also the depth, then you're doing exhaustive search, right? Because you're doing a complete search. So there are intermediates here that are the Monte Carlo research methods. So now let's see if there are questions. Guys, you are only focused on the algorithm, sorry, on the homework. This has been already done because I've given you the code for some things, except that my transition functions are probabilistic. You have to use deterministic transition functions. I don't understand the question, I guess. So, I mean, you can implement that however you want, but yes, you can do it the same way I did. Yes, you can assume this. If it's easier for you, you can assume this. Actually, it's better if you do this in order to reduce also the transitions that you can have. Otherwise, your policy iteration algorithm will explode. Questions on these curiosities? No. Actually, Monte Carlo research, it's something that you should keep in mind, because this is the algorithm that, in conjunction with deep learning, allowed AlphaGo to win. So AlphaGo, the first software that has beaten a human player, I mean, the best human player, the game of Go, was using Monte Carlo research. So this is what we are describing today is state-of-the-art technology, in the sense that these are old methods that, if used in conjunction with some powerful um, uh, neural network, then you can get very exciting things out of them. So I can describe a bit how this was used in that software in AlphaGo. So as I described here, in Monte Carlo research, differently from standard rollout methods, you retain value estimates. So you don't discard them. You only you discard the tree, but you don't discard the value estimates. So what did they do was learning a value function using a deep neural network, and learning also the policy that was being used for the rollout. So they basically did learning on these two objects in a standard, let's say, deep reinforcement learning way. So using reinforcement learning with um, in conjunction with neural networks, and basically this was used on top of standard Monte Carlo research with UCB tree policy. So actually, let me say that the Monte Carlo research with UCB tree policy is called upper confidence bound for trees. Specifically, it's called UCT algorithm. And Yeah, that's really it. There is a paper that is available if you want. You can read that. I can also add that on Classroom for reference if you're interested. Okay. So let me see if in the manual we got any new questions. Only on the homework. Should we use the gym for the environment, or can we use the NMAS in your exercises? I mean, this is clear in the description of the homework. You should use gym. Otherwise, you're not, if you're not respecting the description of the homework, then you will not get the points for it. Okay, so given we don't have questions, let's move on to the next topic. So there are, in this set of slides, you will see uh, two different topics, one of which has very few slides, but will be very useful for your projects, and the other one, which will be a very important part to understand for your projects again. So I will try to spend some time on both these topics. Specifically, I think I will not start the policy gradient methods until next class because they require to spend a bit of time on them. Actually, note also that this is the last set of slides, of theory slides that we will do, because then we'll try to be a bit more hands-on, or also we'll try to look at some papers that will be the ones that you will use for your projects. But let's start with the function approximation side of things. So far, both for the model-free and the model-based methods, we have described all our algorithms in terms of tables. We have said we have a Q table, we have a table that represents our models, and so on and so forth. And time by time, I have said, but look, specifically when we were looking at the code in the examples, in practice, if you're using a neural network or a function approximator, this is how you can build your optimization process. Specifically, what I did is specifying every algorithm in terms of targets, right? I have said that we have the Monte Carlo target, we have the TD target, where we can have the Q-learning target, the SARSA target, the expected SARSA target, so on and so forth. But I said every algorithm has the same structure for the update. The only thing that changes is this target. Now, when we use function approximators, like, again, neural networks, you can only cast your problem in the form of a supervised learning problem, right? So how can you cast this problem in the form of a supervised learning problem? Simply, you will try to fix the error. You will try to minimize the error between the target and your current prediction. So this means creating generally an L2 loss, so a mean-square error loss, a Huber loss, whatever you prefer, a loss that is minimizing this distance, this error between the target and the prediction. Okay, so this is, again, the general structure for tabular methods was the one that I usually described. So next estimate becomes previous estimate plus alpha that multiplies target minus current prediction. In the supervised learning setting, basically we'll have always the difference between the target and the current prediction to be, for example, computed as a mean square error or Huber laws or something like that. So this is the general structure. Again, also here, the only thing that changes is the target. Now, the problem is slightly more complex, not slightly, it's quite more complex in the fact that given that we are incrementally acquiring data, we're dealing with non-stationary distributions and specifically data that are not IID. IID means independent and identically distributed. For example, last week when I was showing you the code for the Q-learning, I said if you were using a neural network, you would use something called an experience replay to correlate your data. Because experience replay is nothing else than a buffer where you put your data and you sample from there in order to have more decorrelated data. The other thing that I said is that in order to have not always a moving target, but a target that you can reach and then move, you typically use, for example, two function approximators for the Q function, and one will be the one generating your target, the one that you use to compute your target, and the other one is the one that you are optimizing. And then time by time you merge them. But all in all, what you're doing when you're using function approximator is minimizing the mean square error between the true value, the one that you have in your, the true value that you are trying to estimate, and the approximate value. So that's on the optimization side of things. Now, in order to do optimization, you need to be able to represent a function, right? So your neural network will represent a function because that's why it's called a function approximator. But learning a function based on just the states as you get them from the environments can be pretty complex, right? Let's say, for example, that you're getting observations that are very, for example, you have a continuous environment like this room again, and your robot is moving around the room, then you can use the coordinates x, y, theta of your robot, and you can use the velocity, the angular and the linear velocity of your robot as the state. Now, it's not too complex, but still, it's quite hard for a function approximator to learn this. Why, when I say it's quite hard, I mean that a function approximator will need a lot of data in order to learn that. So neural networks specifically are not sample efficient, meaning that they require a lot of data in order to learn something well. If we're doing deep reinforcement learning, that's a problem. So one thing that you want to do is try to represent your states in such a way that it's easier for your function approximator to generalize better. And you should have seen this also in the other part of the machine learning course, that representing features well is key, is very important in order to allow your function approximator to learn well. So given some state representations, what are possible ways that we can uh, change our state to compute some features that are easier for the function approximator to learn? Specifically here, we have a bunch of examples that are commonly used in reinforcement learning, which are polynomials, Fourier basis, coarse coding, tile coding, and RBFs, radial basis functions. So polynomials, I think you have seen this also in machine learning. The other part is, so it's very simple, right? You just compute some polynomials at a certain degree that you choose given your state. So how do you do that? Let's say S is your state, then S will be composed of several elements. For example, if you have the position of your robot will be composed of three elements, S1, S2, S3, which will be X, Y, and theta. Right? So your state that represents the position of your robot will be composed of three elements, right? So uh, in this example, I'm assuming you have only two elements, for example, X and Y, and you can compute polynomials out of this as just having one, which is S elevated to 0, then S elevated to 1, so S1 and S2. Then the product between S1 and S2, elevated to by 2, so S1 squared and S2 squared. Then S1 that multiplies S2 squared, and so on and so forth. So all the possible combinations of these polynomials, simple polynomials. Uh, they are very easy to compute. They don't work great, also because you don't, I mean, maybe these features are more discriminative than just X, Y, theta, for example, but I mean, they might add some degree of complexity sometimes, and they don't really use any concrete abstraction, right? They can be useful, but they don't really represent well anything that we might be interested in. Uh, something that works much better instead is called Fourier basis. So this is also a very common and easy featureization of states that performs quite well in several problems. So let's say that your state is uh, between 0 and 1, and if it is not in 0 and 1, you can of course force that to be between 0 and 1. And then you have a certain number of C's that you can see here, C's that you can choose between 0 and n. Then you can build several features where your feature will be the cosine of your state that multiplies this every C, uh, and that's it. So what is this doing? Is basically highlighting um, the behavior of your state at different frequencies. Huh? It's showing you the let's say the spectrum of your state. So this is in one dimension. You can do this in several dimensions. So if your state is multidimensional, you will use a C that has the same dimension as your state. So it's a vector. And then if it is 0, 1, for example, you will get something like this. If it is 1, 0, it will be something like this, and so on and so forth. Again, this is, you should think about this as a filter that highlights the behavior of your state at different frequencies. So if you look at the mean square of your value estimate over different episodes by using on the same problem a polynomial basis and a Fourier basis with the same function approximator, you will see that the Fourier basis one will behave much better because the features that you compute in this way are more discriminative. They separate your state on different frequencies in this case, while the polynomial basis is much less discriminative. Another kind of featureization that is quite common and is one that you will see in several examples also online. For example, if you look at the OpenAI Jim's Monte learning problem, which you will work on as well for your project, you will see that tile coding specifically, which is a form of coarse coding, is commonly used. So this is used specifically for problems where your state space is continuous. And the idea is to discretize your state space using circles. So if this, the idea is that if the state is inside a circle, then your feature will be 1, otherwise it will be 0. Of course, there will be some possible overlap, and how you choose to locate so the um, how you choose to collocate your circles will change the number of features, but also they overlap, the way they overlap. So let's look at this example here. So here I have said that if you have well-distanciated circles where there is just a minor overlap between them, then there will be a narrow generalization. What do I mean here? I mean that this state falls only in these 3 circles. So only these 3 circles will share the same information. And so the way they will generalize is that everything that is contained in these 3 circles will sort of share something. If we have more circles falling one on the other, right, then you have a broader generalization because one state will fall in many circles, which means that the information contained in one state will be generalized also to other states. And again, this is features that are 0 and 1. So that's why this kind of generalization works this way. You can also have asymmetric generalization basically by changing the shape of your um, coarse coding. So tile coding is a form of coarse coding, which is, however, more efficient. So the idea is that instead of using circles, you will use squares, tiles, and um, this is just much more efficient to be computed. So basically you have again your continuous state space, you discretize this in the form of a grid, right? And then you have many grids overlapping one to the other. So this will be one tiling, the yellow one will be another tiling, the red one will be another tiling, and this will create an effect similar to the circles where every square in the tile will be on each different tile will be overlapping and sharing some information. So what it will fall in this set here will generalize. And again, you will use 1 and zeros. So for every state, in this case, specifically, you will have 4 active tiles, which means 4 features will turn on when this state is visited. Um, So you can see here that if you look at the mean square error, having more tiles reduces the error in learning over the same amount of episodes compared to having one single tile, which is a simple discretization in the form of a grid. Okay. Again, why do you want to do this discretization? You want to do that in order to collect all your state, try to share information between them, and allow your function approximator to generalize in a more easy way. Huh? So if we look at the generalization that we get with tile coding, this is the generalization if you use uniform offsets between your tiles. So you see that the offset is uniform. If you don't use uniform offset, but an asymmetric one, you get a better generalization because here the information is shared only in a diagonal direction. Here the information is shared in a more homogeneous direction. Another um, feature representation that you can use is called radial basis function. This is, again, actually one of the most important. So the ones that you will certainly see in your future are tile coding and RBFs. So the RBF is nothing else than a Gaussian. So you're computing your uh, the probability of your state of falling in a certain Gaussian. Hmm? So it's like your state is a point in a certain Gaussian, and you're seeing the probability of the point, the probability of that point according to your Gaussian. So this Gaussian, of course, has the usual parameters, which is the mean and the standard deviation. But these are predefined, and are pre-specified. You choose them, and this will represent your Gaussians. Of course, your this is seen in one dimension. You will see that you can do this in several dimensions. So you can have 2D FBFs and so on, so forth, expanding on several dimensions. Mm. So if you are dealing, for example, with a robot roaming in the environment, as our common example, then your state below as is three-dimensional, then you will have a three-dimensional Gaussian norm that you're using. Okay, so these will be basically your pre-processing functions, right? So if you recall, in my code, I had a function that was called pre-process state. So if you replace your optimization part with a neural network and you replace your preprocessed state with some of these functions, then you are done. That's the way you can use a function approximator in order to learn your value function or eventually your policy, now that we'll talk about policy gradient methods. And I think for this part, that's it. Let's see if there are questions. Otherwise, I'll just describe the idea of what policy gradient methods do, and then we'll go into details next lesson. Questions? Non è chiaro niente perché è chiaro tutto. Come? Ah. Okay, I mean, if you have questions, please post them before the end of this class, which I think will be at most in 10 minutes. Okay, so we are again in the land of model-free reinforcement learning algorithms, although not necessarily in the sense that as value, action value and value-based methods apply also to model-based algorithms, in a similar way, this will apply also to model-based algorithms, although we'll cast the problem in the form of a model-free problem. So we don't care about learning a model. We say, we assume that the model is unknown here. So we have seen a bunch of methods that belong to action value methods, right? So we have seen Monte Carlo methods, temporal difference methods, we have seen n-step bootstrapping methods. Those are all action value or value-based methods. So where we directly estimate a value function and then we use this value function in order to compute our policy. In policy gradient methods, similar to what we have seen for bandit problems, instead of learning the value function, we directly learn a parameterized policy. So we directly try to learn the policy. This policy will have some parameters. These parameters will be called theta, which, for example, theta can be the weights of our neural network if the policy is a neural network. And this policy will select the action without looking at the value function. So what we did until now for value function methods was looking at the value function, then being greedy with respect to this value function. Now we directly learn the policy. So this doesn't mean that we don't use at all a value function. This value function may still be used to learn some policy parameters, but is not used for the action selection. So the action selection is done directly by a policy, which is computed separately from the value function. So similar to what we do for what we said for the value functions, we also can learn the policy using a function approximator, and this function approximator again will be characterized by some weights, which will be the parameters of the policy. So this here will go more in detail next time, but we can say that basically policy gradient methods learn the policy directly, as I just said, but based on some cost function, as usual. So this cost function is the metric that gives us the notion of how good the policy is behaving. So we try to optimize our policy with respect to this cost function, and we try to maximize the performance using gradient ascent in this case. So gradient ascent because we want to maximize minimize the cost. So if this is the cost, then you will do gradient descent. If this is something else, like for example the value function, you want to maximize the value function, and then you will do gradient ascent. So it's a performance function. You want to maximize your performance, decrease your cost. Again, let me repeat this. If this is a cost function, then you do gradient descent. If this is a performance function or a value function, then you do gradient ascent. Okay. Then we'll go more in details on this slide next time, but let me show you basically what we are going to do. In policy gradient, as I just say, what it changes is the action selection. The action selection means that while in methods like Q-learning or deep Q-learning, you have to compute the Q values for all the possible actions and then do select the maximum one, the action that gives you the maximum Q value. Here, you have just a policy that will tell you go left, for example. Why do we want to do this? First of all, because it's easier, specifically when you have large action space or continuous action spaces. So far, we have said we're using discrete action spaces where the actions are discrete. In practice, you might have continuous actions, and then computing the max for the Q value, it might be, it's basically impossible or very difficult. While this is much easier in the case of a policy gradient method where you have your policy directly selecting the action. One other reason for doing this is that value-based methods sometimes, not always, can be much more unstable. So if we look at this example specifically, let's say that we are in this small grid world where we have a short corridor where we get -1 reward per step. The actions are go right and go left, and the effects are the normal ones in the first and in the third state, meaning that if I go left, I go left. If I go right, I go right. But in this second state, the effects of these actions are reversed. What do I mean? I mean that if I go right, if I select action go right, then I will go left, and vice versa. The other issue here might be specific in this scenario is that we are using a featureization for which all the states appear identical. So a featureization of this of every state, if I select action right, is 1, 0, and a featureization of every state, if I select action left, is 0, 1. So there is no way for the agent to discriminate between the first, the second, and the third state, which is a problem, right? Because what should I do then? If we use a value function method, the best thing that we can do is um, either go left or go right. So we can be greedy, right? Compare with respect to our value function. If we are greedy with respect to our value function, either we will go left or we will go right. We can be epsilon greedy at most, which means we have this epsilon component that will let us go uh, um, either left or right randomly. But what would be the optimal behavior here? Would be just going randomly left or right, because we don't know what is the best action. So we shouldn't commit to any action here. So this is not possible in the case of the value function method, while this is possible in the case of a policy gradient method. And specifically, a policy gradient method will say just choose this action with probability 0.5. So the policy will just be with probability 0.5, you will go left, and probability 0.5, you will go right. You want maybe to go right slightly more often because you have the goal on your right. So that's why you have this slight deviation from 0.5. But um, that's the overall idea. So if you change the value function here, you're basically oscillating between going always left and going always right. If you're instead using a policy gradient method, then you are behaving slightly better, and actually you are getting the optimal stochastic policy. Another reason for which you want to get to use policy gradient methods sometimes is that policy gradient methods have better convergence properties. As I just said, in the value-based methods, you can have big oscillations while training. For example, in this case, you will just oscillate between going full left or full right. So there will be a lot of oscillation in the behavior. Instead, so for example, your actions can change in a dramatic way for any small change in the action value. Because, for example, maybe your value will be estimated around here, but if you slightly change this and this in this direction or in this direction, then your actions will change going fully left or fully right. Instead, in policy gradient methods, you don't have this behavior. You just try to ascend your gradient. You follow your gradient in order to find the best parameters that are at least guaranteed to converge a local maximum, or in general to a local maximum, but also to a global maximum. The problem is that in general you converge only to a local optimum, which is a problem. So how can you get out of local optima is using, for example, some exploration that will allow you to explore new states that will get you out of this optima, of these plateaus in your performance function. This said, I will stop here, saying uh, why we want to do policy gradient methods, and we'll see how to do this next time. If you have questions, please ask them now regarding also this topic. Otherwise, in 5 minutes, I will close the lesson. Okay, I mean, I don't see questions coming, so I guess we can close it here and see you next Monday.